So what are we going to do today? We just finished a whole overview on Kabbalah, and now we're going to try and go back and dig into it a little bit more. But we're going to do this in a different way to try and tie it together with what we did earlier. We're going to go back and revisit the observations that Ron Cowan did, where we ended up with a 26-dimensional space. And we're going to talk about that for a while and what that might have to do with this. And then what comes out of that is the issue of that there's information everywhere. So there's algorithms and there's data, and the algorithms work on the data and actually run the whole universe around us, which is really an amazing observation that Ron came up with. And so having said that, then we're going to go off and look at a physicist's view of this. And the physicist's name is Stephen Wolfram. Now, Stephen was born in 1959 in London of a Jewish family. And in 1920, when he was 21 years old, in 1980, he was made a professor of theoretical physics at Caltech, which is one of the strongest places on planet Earth for doing theoretical physics. And he received a MacArthur Award. MacArthur Award is given out by the MacArthur Foundation to people that are viewed as quote unquote geniuses. And they don't fit into any category. So they give them enough money to live for 5 years pursuing whatever they want to do. So he had a grant to go do this in 1980. And he started working on it, and he decided to drop out of physics. It isn't that he lost interest in physics, he got interested in computers and what came with that. So he started to really dig into computers and software. And the net of it was in 1986, 1987, he founded a company, which I think is called Wolfram Research. So it's his name. It's in Urbana, Illinois, where the University of Illinois is, its main campus. And he created a product called Mathematica. Mathematica is software that allows you to do not simply crunch out numbers, but it allows you to deal with symbols. So if I gave you an equation like ax plus b equals c, if I just gave you that, then, and it said, what is x? Then it would come back and say x equals c minus b all divided by a. It would take those symbols. And then if you wanted to, you could put some numbers in there to see what you would get out. But it does everything symbolically. He's now on his 13th release of this software. The company is up to $100 million a year in revenue. And he's been using the money to go fund not simply the software product, which has thousands of functions in it now, but also to go fund, he's got his own search engine now, different than Google, which he called Wolfram Alpha. And so you can go to his website and play around with Wolfram Alpha and see what capabilities it has for doing search. And then he decided to go back into physics after all of this. And he decided that really what physics needs is a new viewpoint, is to go back and try and include much more things based on algorithms and rules. So he calls this the Ruliad, for R-U-L-I-A-D, Ruliad, for the rules of rules. And that is why we're going to talk about him, is because of what Ron Cowan observed with the fact that information is controlling everything. Wolfram on his own came to the conclusion that what physics needed was to take the view of these things based on algorithms and the things that go with them. Now, the thing about the algorithms that we'll see is what Wolfram does is he generates patterns, geometric patterns. And the geometric patterns give him insight into what the physical phenomena is. I'm not saying this does it for everybody. That's what he says he gets out of it. But the point in all this is that when we were looking at Kabbalah, we had the notion of the tree of life. and it was a geometric representation of 10 nodes or sephirot. And that's where Wolfram is going, is he's looking around to recreate physics. But the underlying mechanism for physics is going to be all software. It's going to be all algorithms for doing these things. So since we're doing this, I'm going to just kind of wrap up the discussion there by going into two people in the 20th century, Kurt Gödel and Alan Turing, who were really the founders of what today would be called computer science. And we'll see what they came up with. But the key thing to keep in mind there is, while we're doing all these algorithms, Gödel and Turing posed the question of, suppose I gave you an arbitrary computer program. How would I know that that program was able to stop? Why wouldn't it simply run forever? Okay, why wouldn't it simply run forever? And this sounds like, well, who cares? But when you actually start to think about it, you know, it turns out that this is a very tough question to go answer. And in fact, what Gödel and Turing both showed was that you can't answer this question. That question is not known within the framework of, say, any software that you wrote or any system that you have there. It's a meta question. It's something that goes above and beyond anything that you could think of. And we'll see that when we go through what they're doing. And then finally, what we're going to do is go back now to the tree of life. And we're going to look at the sacred geometry for the tree of life. And you'll see pictures there, geometric pictures that come out of the tree of life. And we'll be following the work of Stephen Phillips, who is a British physicist that interacted with Ron Cowan in the 1990s timeframe. And you'll get some idea of how in the world Kabbalah and information and algorithms and computers all come together. So that's where we're heading tonight. I'm trying to give you some
I just want to
heads up. Go ahead.
There that the Jewish mystical view is that the universe is created with letters, and numbers are the same, and the Hebrew alphabet also represents numbers, not just 1 through 22. Different letters represent different numbers, but they see the whole thing, and they have for millennia as kind of this code that's what creates reality. So they've been saying this for a long time.
Yeah, we're going to see that Gödel said the same thing, and Turing. So we're just going to do a little review here. Way back in our second module, we argued that there was a 26 real dimensional space that makes up the universe, and we live in we're matter, and we live in a 10-dimensional subspace of the 26 dimensions. There's a second 10-dimensional subspace for dark matter. That's where spirits or souls live. And then there are these funny, what are called compactified dimensions that we can't really see. We don't have the instrumentation right now, but I'm sure once you point out to people that there's something there, they'll go find out how to go actually measure this. So we have 6 of our 10 dimensions are all compactified dimensions. They're very small. You could think of them as wrapped around the X, Y, and Z axes. And there's actually 2 of them wrapped around the X-axis, 2 around the Y-axis, 2 around the Z-axis is a way to think of this. And they're very small. And the same thing is true for dark matter. And then there's a final six-dimensional compactified space that connects all these things and is used for synchronization. The universe has to be able to function. So what it looks like happens here is that information signals fly around in these compactified dimensions and actually go faster than the speed of light, because they're not in the dimensions that we're in, they're in these other dimensions. And they go instantaneously, so there's no delay, so the universe doesn't get out of sync. And the next,
in one dimension, something could be 10 miles apart, but if you fold up the dimensions, it could be 2 inches apart,
or two microns or two
Right.
whatever. So what we came up with here was, well, the 10-dimensional space that we're in has 3 holes in it. There's actually holes in these compactified dimensions. Well, where do the holes go? Well, there's 3 holes there, and we notice the dark matter has 4 holes for its 6-dimensional compactified dimensions. And at the bottom, we notice that the synchronized dimensions have 8 holes. So it looks like 3 of the holes go from matter down to the synchronization. So that means we lost 3 of the dimensions, okay? They're tied together through the holes. And then we have 4 of the holes goes down to the synchronization, which has 8 holes. So we lost another 4 dimensions. And then finally, there's 1 hole, but we've got a bunch of dimensions that we can connect. You know, we can connect dimension 1 and dimension 5 together, and so we lose a dimension by connecting them together. So if we took the 3 times 6 or 18 dimensions and we connect them all together with holes, we end up with 10 dimensions. So it looks like what the Kabbalah, what the Kabbalah is saying is that this is the higher realms. These are the realms where the Buddha, where Jesus of Nazareth was operating, and this is where you can actually control the forces and the particles in the space that we're in, the 4 dimensions of space and time, and so forth. And so we want to just keep that in mind. I'm going to skip forward here a second. These are all observations that we saw before that Ron made. Hold on, just have to get there. We've got, here it is.
Cut through the
Hold on.
dimensions.
Here it is, here it is. So what we have here is a different way of trying to say the same thing. In the world of science, the most fundamental thing that people deal with is physics, which deals with the particles and the forces. And so that's at the bottom of these 2 rectangles. And the most fundamental particles are vibrating strings. In the space of matter, there are 10 strings, and they make up what are called subquarks. And then there are bosons and electrons. And that's all of physics is there with those particles, and the bosons give us the field. The only difference with dark matter is the strings only have 5 strings. The subquarks only have 5 strings, and there isn't any electron there. Okay, so that you're dealing entirely with subquarks, which are really pieces of the nucleus. So that's at the bottom of the pile. And then above it, then we have chemistry. So in our world, the chemistry is really the electrons. A hydrogen atom has 1 electron and a nucleus. A helium atom has 2 electrons and a nucleus. A lithium atom has 3 electrons and a nucleus. So it's the interaction of the electrons there that make up the materials that we see around us in chemistry. The difference in dark matter is that because there's no electron, these subquarks just combine together, and they combine together like coral does, or like a fungus does. So you end up with these branching trees that are all on the subnuclear scale. And remember, the thing that I tried to point out before, if we look at a single atom and we ask, you know, the atom is the size of the basilica in the Vatican for St. Peter's, then the nucleus of these atoms is the size of the chalice that's there on the altar. So it's incredibly small compared to the action of the electrons. So the dark matter is just made up of things that go into the nucleus and is very, very teeny, okay? And then on top of that, we have a different sort of chemistry, which is biology, where we take these chemicals and we end up with the DNA and RNA that are going to control how things work. But there's also actually an electric field there that's generated by the cells that goes with us, as we'll see. And I simply labeled this as mortal, ashes to ashes and dust to dust. So this will be born, and the cells will grow, and then they'll die, and at some point everything dies, and we start over again. Whereas the dark matter ends up just being immortal. It's either sentient, it's alive, it's got some heat, some sort of activity that it draws on to energize it, or it's just quiescent, it's just asleep. It could be drifting in between planets is a standard thing. There's a lot of dark matter out there in space. And the thing to keep in mind when it comes to matter versus dark matter is if the ratio is basically 1 to 5. Matter is 1 and dark matter is 5. It's 5 times more common than matter in the universe that we're in. Now, all of this is controlled by the information flow that we talked about with those compactified dimensions. And that occurs all through this thing. And the level of physics, the level of chemistry, the area of biology, it's underlying everything. And this is the fundamental controlling mechanism for the entire universe that we see around us. And this is, again, all due to these observations that Ron Cohen did. So now what I'm going to do is I'm going to go back over to our website. Let's see. This is not here. I want to go to
Our site?
Hold on. That's what I hate about this thing.
There's got to be a better
No,
way.
It just decides to. Here it is. Okay, now I'm gonna go back here.
We spent a weekend on that chart trying to get the concepts really clear. So
Right. Why? Oh,
We-
I'm gonna
we
get
hope it
in
helps.
out of screen share. Okay. Now I'm gonna go back into, here we go. Why does this thing, here we go. Now this is a TED talk by Stephen Wolfram, and he'll be talking about his software product Mathematica for doing symbolic manipulation of mathematical expressions. He'll be talking about his Wolfram Alpha search engine, and then I'll be talking about what he called a new kind of science. So this will be the science that we're looking at, the algorithms that are generating the world around us. It'll generate space and time. It'll be underlying everything. That's why I tried to picture information as being at the bottom of everything. So here we go.
It's kind of like the Matrix.
It's a big idea. Actually, I think it'll eventually be seen as probably the single biggest idea that's emerged in the past century.
Can you
It's
hear
the
it
idea
well?
of computation. Now, of course, that idea has brought us all of the computer technology we have today and so on. But there's actually a lot more to computation than that. It's really a very deep, very powerful, very fundamental idea, whose effects we've only just begun to see.
No,
Well, I myself have spent the past 30 years of my life working on 3 large projects that really tried to take the idea of computation seriously. So I started off at a young age as a physicist, using computers as tools. Then I started sort of drilling down, thinking about the computations I might want to do, trying to figure out what primitives they could be built up from and how they could be automated as much as possible. Eventually, I created a whole structure based on symbolic programming and so on that let me build Mathematica. And for the past 23 years, at an increasing rate, we've been pouring more and more ideas and capabilities and so on into Mathematica. And I'm happy to say that that's led to many good things in R&D and education, lots of other areas. Well, I have to admit, actually, that I also had a very selfish reason for building Mathematica. I wanted to use it myself, a bit like Galileo got to use his telescope 400 years ago. But I wanted to look not at the astronomical universe, but at the computational universe. So we normally think of programs as being complicated things that we build for very specific purposes. But what about the space of all possible programs? Here's a representation of a really simple program. So if we run this program, this is what we get. Very simple. So let's try changing the rule for this program a little bit. Now we get another result. Still very simple. Try changing it again. Get something a little bit more complicated, but if we keep running this for a while, we find out that although the pattern we get is very intricate, it has very regular structure. So the question is, can anything else happen? Well, we can do a little experiment. Let's just do a little mathematical experiment, try and find out. Let's just run all possible programs of the particular type that we're looking at. They're called cellular automata. You can see a lot of diversity in the behavior here. Most of them do very simple things, but if you look along all these different pictures, at rule number 30, you start to see something interesting going on. So let's take a closer look at rule number 30 here. So here it is. We're just following this very simple rule at the bottom here, but we're getting all this amazing stuff. It's not at all what we're used to. And I must say that when I first saw this, it came as a huge shock to my intuition. And in fact, to understand it, I eventually had to create a whole new kind of science. This science is different, more general than the mathematics-based science that we've had for the past 300 or so years. You know, it's always seemed like a big mystery how nature, seemingly so effortlessly, manages to produce so much that seems to us so complex. Well, I think we found its secret. It's just sampling what's out there in the computational universe, and quite often getting things like rule 30 or like this. And knowing that starts to explain a lot of long-standing mysteries in science. It also brings up new issues, though, like computational irreducibility. I mean, we're used to having science let us predict things, but something like this is fundamentally irreducible. The only way to find its outcome is effectively just to watch it evolve. It's connected to what I call the principle of computational equivalence, which tells us that even incredibly simple systems can do computations as sophisticated as anything. It doesn't take lots of technology or biological evolution to be able to do arbitrary computation, just something that happens naturally all over the place. Things with rules as simple as these can do it. Well, this has deep implications about the limits of science, about predictability and controllability of things like biological processes or economies, about intelligence in the universe, about questions like free will, and about creating technology. You know, in working on this science for many years, I kept wondering, what will be its first killer app? Well, ever since I was a kid, I'd been thinking about systematizing knowledge and somehow making it computable. People like Leibniz had wondered about that too, 300 years earlier. But I'd always assumed that to make progress, I'd essentially have to replicate a whole brain. Well, then I got to thinking, this scientific paradigm of mine suggests something different. And by the way, I've now got huge computation capabilities in Mathematica, and I'm a CEO with some worldly resources to do large, seemingly crazy projects. So I decided to just try to see how much of the systematic knowledge that's out there in the world we can make computable. So it's been a big, very complex project, which I was not sure was going to work at all. But I'm happy to say it's actually going really well. And last year, we were able to release the first website version of Wolfram Alpha. Its purpose is to be a serious knowledge engine that computes answers to questions. So let's give it a try. Let's start off with something really easy. Hope for the best. Very good. Okay. So far, so good. Let's try something a little bit harder. Let's say, let's do some mathy thing, and with luck, it'll work out the answer and try and tell us some interesting things about related math. We could ask it something about the real world. Let's say, I don't know, what's the GDP of Spain? And it should be able to tell us that. Now we could compute something related to this. Let's say the GDP of Spain divided by, I don't know, the, let's say the revenue of Microsoft. The idea is that we can sort of just type this in, this kind of question in, however we think of it. So let's try asking a question like a health-related question. So let's say we have a lab finding that, we have an LDL level of 140 for a male aged 50. So let's type that in, and now Wolfram Alpha will go and use available public health data and try and figure out what part of the population that corresponds to and so on. Or let's try asking about, I don't know, the International Space Station. And what's happening here is that Wolfram Alpha is not just looking up something, it's computing in real time where the International Space Station is right now at this moment, how fast it's going, and so on. So Wolfram Alpha knows about lots and lots of kinds of things. It's got by now pretty good coverage of everything you might find in a standard reference library and so on. But the goal is to go much further and very broadly to democratize all of this kind of knowledge and to try and be an authoritative source in all areas, to be able to compute answers to specific questions that people have, not by searching what other people may have written down before, but by using built-in knowledge to compute fresh new answers to specific questions. Now, of course, Wolfram Alpha is a monumentally huge long-term project with lots and lots of challenges. For a start, one has to curate a zillion different sources of facts and data. And we built quite a pipeline of Mathematica automation and human domain experts for doing this. But that's just the beginning. Given raw facts or data to actually answer questions, one has to compute. One has to implement all those methods and models and algorithms and so on that science and other areas have built up over the centuries. Well, even starting from Mathematica, this is still a huge amount of work. So far, there are about 8 million lines of Mathematica code in Wolfram Alpha built by experts from many, many different fields. Well, a crucial idea of Wolfram Alpha is that you can just ask it questions using ordinary human language, which means that we've got to be able to take all those strange utterances that people type into the input field and understand them. And I must say that I thought that that step might just be plain impossible. Two big things happened. First, a bunch of new ideas about linguistics that came from studying the computational universe. And second, the realization that having actual computable knowledge completely changes how one can set about understanding language. And of course, now with Wolfram Alpha actually out in the wild, we can learn from its actual usage. And in fact, there's been an interesting co-evolution that's been going on between Wolfram Alpha and its human users. And it's really encouraging. Right now, if we look at web queries, more than 80% of them get handled successfully the first time. And if you look at things like the iPhone app, the fraction is considerably larger. So I'm pretty pleased with it all. But in many ways, we're still at the very beginning with Wolfram Alpha. I mean, everything is scaling up very nicely. We're getting more confident. You can expect to see Wolfram Alpha technology showing up in more and more places, working both with this kind of public data, like on the website, and with private knowledge for people and companies and so on. I've realized that Wolfram Alpha actually gives one a sort of a whole new kind of computing that one can call knowledge-based computing, in which one's starting not just from raw computation, but from a vast amount of built-in knowledge. And when one does that, one really changes the economics of delivering computational things, whether it's on the web or elsewhere. We have a fairly interesting situation right now. On the one hand, we have Mathematica with its sort of precise formal language and a huge network of sort of carefully designed capabilities that are able to get a lot done in just a few lines. Let me show you a couple of examples here. So here's sort of a trivial piece of Mathematica programming. Here's something where we're doing sort of integrating a bunch of different capabilities here. Here we just create in this line a little user interface that allows us to do something fun there. you could go on, that's a slightly more complicated program that's now doing all sorts of algorithmic things and creating a user interface and so on. But it's something that is very precise stuff. It's a precise specification with a precise formal language that causes Mathematica to know what to do here. Well, then on the other hand, we have Wolfram Alpha with all the sort of messiness of the world and human language and so on built into it. So what happens when you put these things together? I think it's actually rather wonderful. With Wolfram Alpha inside Mathematica, you can, for example, make precise programs that call on real world data. Here's a real simple example. You can also just sort of give vague input and then try and have Wolfram Alpha figure out what you're talking about. Let's try this, yeah. And actually, I think sort of the most exciting thing about this is that it really gives one the chance to democratize programming. I mean, anyone will be able to just sort of say what they want in plain language. Then the idea is that Wolfram Alpha will be able to figure out what precise pieces of code can do what they're asking for, and then show them examples that'll let them pick what they need to build up bigger and bigger precise programs. So sometimes Wolfram Alpha will be able to do the whole thing immediately and just give back a whole big program that you can then compute with. So here's a big website where we've been collecting lots of educational and other demonstrations about lots of kinds of things. So I don't know, I'll show you one example maybe here. This is just an example of one of these computable documents. This is probably a fairly small piece of Mathematica code that's able to be run here. Okay, let's zoom out again. So given our new kind of science, is there a general way to use it to make technology? So with physical materials, we're used to kind of going around the world and discovering that particular materials are useful for particular technological purposes and so on. Well, it turns out we can do very much the same kind of thing in the computational universe. There's an inexhaustible supply of programs out there. The challenge is to see how to harness them for human purposes. Something like Rule 30, for example, turns out to be a really good randomness generator. Other simple programs are good models for processes in the natural or social world. And for example, Wolfram Alpha and Mathematica are actually now full of algorithms that we discovered by searching the computational universe. And for example, this has become surprisingly popular among composers, finding musical forms by searching the computational universe. In a sense, we can use the computational universe to get mass customized creativity. I'm hoping we can, for example, use that even to get Wolfram Alpha to routinely sort of do invention and discovery on the fly, and to find all sorts of wonderful stuff that no engineer and no process of incremental evolution would ever come up with. Well, so that leads to kind of an ultimate question. Could it be that someplace out there in the computational universe, we might find our physical universe? Perhaps there's even some quite simple rule, some simple program for our universe. Well, the history of physics would have us believe that the rule for the universe must be pretty complicated. But in the computational universe, we've now seen how rules that are incredibly simple can produce incredibly rich and complex behavior. So could that be what's going on with our whole universe? If the rules for the universe are simple, it's kind of inevitable that they have to be very abstract and very low level, operating, for example, far below the level of space or time, which makes it hard to represent things. But in at least a large class of cases, one could think of the universe as being like some kind of network, which when it gets big enough, behaves like continuous space in much the same way as having lots of molecules can behave like a continuous fluid. Well, then the universe has to evolve by applying little rules that progressively update this network. And each possible rule, in a sense, corresponds to a candidate universe. Actually, I haven't shown these before, but here are a few of the candidate universes that I've looked at. Some of these are hopeless universes, completely sterile, with other kinds of pathologies like no notion of space, no notion of time, no matter, other problems like that. But the exciting thing that I found in the last few years is that you actually don't have to go very far in the computational universe before you start finding candidate universes that aren't obviously not our universe. Here's the problem. Any serious candidate for our universe is inevitably full of computational irreducibility, which means that it's irreducibly difficult to find out how it will really behave and whether it matches our physical universe. A few years ago, I was pretty excited to discover that there are candidate universes with incredibly simple rules that successfully reproduce special relativity and even general relativity and gravitation, and at least give hints of quantum mechanics. So will we find the whole of physics? I don't know for sure, but I think at this point it's sort of almost embarrassing not to at least try. Not an easy project. One's got to build a lot of technology, one's got to build a structure that's probably at least as deep as existing physics. And I'm not sure what the best way to organize the whole thing is. Build a team, open it up, offer prizes, and so on. But I'll tell you here today that I'm committed to seeing this project done, to see if within this decade, we can finally sort of hold in our hands the rule for our universe and know where our universe lies in the space of all possible universes, and be able to type into Wolfram Alpha theory of the universe and have it tell us. So I've been working on the idea of computation now for more than 30 years, building tools and methods and sort of turning intellectual ideas into millions of lines of code and grist for server farms and so on. With every passing year, I realize how much more powerful the idea of computation really is. It's taken us a long way already, but there's so much more to come, from the foundations of science to the limits of technology to the very definition of the human condition. I think computation is destined to be the defining idea of our future. Thank you.
Wow.
So the thing I'd like you to take away from that is, again, notice what he did. He wrote some software, but in doing this, he was always looking at pictures, at some sort of geometric representation of what was going on to guide him in what he was doing, again and again. And he's skipping over so many steps, but you know, it is what it is. So I think that he's onto something here that will capture the essence of what Ron Cowan observed about how this information is really at the most fundamental level of governing things. And I'm just going to run off now to do another.
These are all resources on our website.
Yeah,
by the way.
these all are coming off of the website. Okay, so I'm going to.
So you should poke around in there.
Right. So now I'm just going to go back to screen share. And we're gonna look at what Kurt Gödel did. Some background here. You know, many of you have taken a geometry class where you dealt with Euclid. So if you remember anything, Euclid had a set of axioms. There were 5 axioms, and then with those 5 axioms, you would prove different things along the way. So, for example, the sum of the angles of the interior angles of a triangle in a plane was always 180 degrees, if you remember that. So there were a bunch of these things there that came out of these 5 axioms, or to put it differently, the hundreds of theorems that Euclid proved were all really contained in the 5 axioms. There was nothing new. If you really understood what the 5 axioms did, you were there. There was nothing more to do. So a German mathematician, David Hilbert, proposed in the year 1900 that we should try and come up with the axioms for all of mathematics. And he thought this would be a really challenging problem and would lead to some interesting things. Gödel showed that was impossible. Okay, that you're going to be able to come up with statements that you just can't say anything about. That's why it's called his incompleteness theorem. So let's take a look at what Gödel did here.
Consider the following sentence. This statement is false. Is that true? If so, that would make this statement false. But if it's false, then the statement is true. By referring to itself directly, this statement creates an unresolvable paradox. So if it's not true and it's not false, what is it? This question might seem like a silly thought experiment, but in the early 20th century, it led Austrian logician Kurt Gödel to a discovery that would change mathematics forever. Gödel's discovery had to do with the limitations of mathematical proofs. A proof is a logical argument that demonstrates why a statement about numbers is true. The building blocks of these arguments are called axioms, undeniable statements about the numbers involved. Every system built on mathematics, from the most complex proof to basic arithmetic, is constructed from axioms. And if a statement about numbers is true, mathematicians should be able to confirm it with an axiomatic proof. Since ancient Greece, mathematicians used this system to prove or disprove mathematical claims with total certainty. But when Gödel entered the field, some newly uncovered logical paradoxes were threatening that certainty. Prominent mathematicians were eager to prove that mathematics had no contradictions. Gödel himself wasn't so sure, and he was even less confident that mathematics was the right tool to investigate this problem. While it's relatively easy to create a self-referential paradox with words, numbers don't typically talk about themselves. A mathematical statement is simply true or false, but Gödel had an idea. First, he translated mathematical statements and equations into code numbers, so that a complex mathematical idea could be expressed in a single number. This meant that mathematical statements written with those numbers were also expressing something about the encoded statements of mathematics. In this way, the coding allowed mathematics to talk about itself. Through this method, he was able to write, "This statement cannot be proved," as an equation, creating the first self-referential mathematical statement. However, unlike the ambiguous sentence that inspired him, mathematical statements must be true or false. So, which is it? If it's false, that means the statement does have a proof. But if a mathematical statement has a proof, then it must be true. This contradiction means that Gödel's statement can't be false, and therefore, it must be true that this statement cannot be proved. Yet this result is even more surprising because it means we now have a true equation of mathematics that asserts it cannot be proved. This revelation is at the heart of Gödel's incompleteness theorem, which introduces an entirely new class of mathematical statement. In Gödel's paradigm, statements still are either true or false, but true statements can either be provable or unprovable within a given set of axioms. Furthermore, Gödel argues these unprovably true statements exist in every axiomatic system. This makes it impossible to create a perfectly complete system using mathematics, because there will always be true statements we cannot prove. Even if you account for these unprovable statements by adding them as new axioms to an enlarged mathematical system, that very process introduces new, unprovably true statements. No matter how many axioms you add, there will always be unprovably true statements in your system. It's Gödel's all the way down. This revelation rocked the foundations of the field, crushing those who dreamed that every mathematical claim would one day be proven or disproven. While most mathematicians accepted this new reality, some fervently debated it. Others still tried to ignore the newly uncovered hole in the heart of their field. But as more classical problems were proven to be unprovably true, some began to worry their life's work would be impossible to complete. Still, Gödel's theorem opened as many doors as it closed. Knowledge of unprovably true statements inspired key innovations in early computers. And today, some mathematicians dedicate their careers to identifying provably unprovable statements. So while mathematicians may have lost some certainty, thanks to Gödel, they can embrace the unknown at the heart of any quest for truth. The Pythagorean theorem has more than 300.
Okay, so there we have this is, let me get it out of, oh, I'm in screen share, that's what the problem is. There you have an indication of something that, this is the mystery of mathematics, is how can you have something that's undoubtedly true, but you can't prove it, okay? Now we're going to go to what Alan Turing did, building on really what Gödel had come up with, and you'll see
Question.
yeah, sure. I was hoping we'd go through this and then we'll stop for questions, okay? So let me, if that's okay. So let me get this cranked up here.
Today we're going to be talking about a problem in logic and how in solving that problem,
Oh, wait,
Alan
I
Turing
forgot
almost
one. I forgot to do one thing. I forgot to go back to screen share. Hold on. Okay, here we go.
inadvertently invented the modern digital computer. So we start back at the beginning of the 20th century, where mathematicians had posed this problem. In logic, we're interested in finding, do these premises entail this conclusion? So premises are the bits you start off with in an argument. They are the bits you know at the beginning, or your assumptions. And the conclusion is the bit you want to establish, the bit that you reason to with your argument. And we want to know, is there a test that will tell us, yes, for sure, these premises do or don't entail this conclusion? Is there an automatic way of finding out whether they do or whether they don't? So that's the problem. It's called the decision problem. The mathematicians wanted to find out, is there an answer to the decision problem for first order logic? That's the kind of logic you learn in philosophy or mathematics at university. So lots of mathematicians were trying to work out, is first order logic decidable? That is, can we automatically test whether the premises entail the conclusion? Alan Turing was one of the first to discover that first order logic isn't decidable. To prove this, it's really difficult conceptually because you have to be able to show no possible program can give you the answer. But how do you do that? How do you show something about every possible program? You can't run through every program one by one. But Turing came up with a brilliant solution. His idea goes something like this. Suppose we have a program, and let's just draw it as a black box. It's going to take some inputs, and it's going to give us some outputs. Our program is going to solve some problem. A problem like, do the premises entail the conclusion? We ask it a question and it will give us an answer, yes or no. Now here's another question we can ask. Let's look at all of those possible programs, and we're just thinking of them as black boxes at the moment. We might want to know, is this program, given a certain input, going to give us an answer? Or is it going to trundle on forever and never give us an answer? That is it going to halt or is it not going to halt eventually? So think about your computer running. You want it to give you an answer, and whether it's a good answer or a bad answer, it's better than no answer. No answer would mean the computer trundles round forever and ever in a loop, and you would just never know whether it's going to finish today, tomorrow, or never. So halting is good. So there's another question we can ask. Given some program and some inputs, will it ever halt? Now it turns out that our logical problem, do these premises entail this conclusion, is very similar to this halting problem. In fact, if we can solve the logical problem, then we can solve the halting problem. Will this program halt on this input? So the clever part of Turing's proof is to show that it's impossible for any machine, however clever it is, to solve the halting problem. That is to tell us whether a given machine with a given input will halt or not. And here's how we did it. Let's suppose we've got a machine or a program that solves the problem for us. It solves the halting problem. Don't worry about how it works. Let's just think of it as a black box, taking a description of a machine and an input and giving us an answer. Yes, it will halt, or no, it won't halt. Just suppose that's possible. call that machine H for the halting problem. If you give me that machine, I can transform it into a different machine like this. I stick some extra bits on it so that if it gives me a yes answer, I make it loop forever without ever stopping. If it gives me a no answer, on the other hand, it's going to halt straight away. Let's call that big machine, the whole thing, H+. Now, here's another question we can ask. What happens if I feed the whole machine into itself? So I'm going to put H+ in here and H+ in here. So the question I'm now asking is, I'm feeding H+ into itself. So I'm asking the question, does H+ halt given input H+? And here's where it all goes wrong. Because if H+ does halt, we get a yes answer, but then it loops forever, so it doesn't halt. On the other hand, if it doesn't halt, we get a no answer, but then it halts. So if it does halt, then it doesn't halt. But if it doesn't halt, then it does halt. Either way, we get a contradiction. It's a paradox. And what that shows is we started off assuming that we can solve the problem. We've ended up with a paradox. So our assumption was bad. It turns out there's no possible machine, no possible program that solves the halting problem. The really clever bit about Turing's idea is it doesn't matter what kind of program or machine is. It doesn't matter whether it's an abstract algorithm, whether it's a real computer, a physical computer, it doesn't matter what it is. We've proved that no such program is possible. Turing, as part of his argument,
Okay, so this is a lot of beef, but we're just trying to set the stage now for looking at the tree of life, the sacred geometry that we saw of the Kabbalah, and then we'll go look at the sacred geometry associated with the Sri Rantra of Hinduism. They're very much related, and you'll see a lot of geometrical activity there. But what I'm arguing here is that the geometry that we see is really all controlled at a higher level by these algorithms. The information that's there creates these structures, and it leads to the things that we see around us, evidently, and it allows everything to be controlled, all the particles and all the fields that are there. But what goes with it is, that we end up with an abstraction, something that's if I was a Kabbalist in the 1400s in Spain, there's no notion of computers then, and algorithms and information, and so they would come up with geometric representations. What we saw, this tree of life, and as we'll see, there's a lot of geometry that underlies the tree of life. All that I'm arguing for here is that the geometry that they're going to be talking about is actually controlled by what we think are going to be some pretty simple algorithms that generate some amazing, very rich behavior, which is in fact the universe around us. So that's where we're heading with this stuff. Questions?
So any questions?
Yeah, you can go look at this stuff and see, but you'll see, the part of the problem here is when you deal with these ideas, which everyone, somehow thinks they have a handle on it. The question of, could I write a program? If I gave you a program, how would I know that it halts? Is there some test I could do on it? We just saw the answer was no. It's a meta question. We have to be outside the universe to be able to go answer that question. This is the mystical side of mathematics. Okay, is like where are you? You're in hyperspace somewhere. So
is it kind of like Schrodinger's cat?
No, Schrodinger's cat is different. This is that's what Ron Cowan showed was that the information controls the idea in the Schrodinger cat activity is that there's a cat in a box and there's a little container of deadly toxic nerve gas, but it's all sealed up. But there are particles blasting through the side of the box, and these are cosmic rays, for example, and one of them might trigger the ampule that holds all this terrible nerve gas opening up and killing the cat. So now we open the box up, and the question is the cat alive or dead? Yes or no. Either the cat got gassed by this stuff or the cat didn't get gassed by it. But that's something that Ron observed was controlled by the information flow that would determine was there something that would actually do this. The question we're asking here is beyond that, which is like is there is there any way to answer the question that we're even talking about? So it's I'm just trying to set the stage for this. You can go look at this on the website. There's a lot of material there. And now what we're going to do is we're going to go back to the website, and we're going to pick up.
This is our website. Just scroll up to the top so people can see. That's it.
No, we're not in screen.
illustration
We're not in screen share.
Oh,
Hold on. I'll go back to screen share so you can see what we're doing. We're here on the website. So what I just did.
that's an illustration of Ron's of the crown chakra.
Yeah. And
these
here,
are all illustrations of him.
yeah, these are all things from Ron. And then
We have to talk to Bruce about any copyright issues.
we've got
But
these
we
are the
wanna
three.
help get his ideas and his work out there.
Right, these are the three videos we just looked at. The one by Wolfram, which is the TED Talk, and then the one on Gödel's incompleteness theorem and Turing with the halting problem. So that's what we did to set the stage here. Now back up here. I have to go back up.
Those are the branches of the dark matter.
Yeah, this is what dark matter turns into, morphs into. All of these things are there. I'm just going back up here to get to this, which is what Stephen Phillips came up with. Okay, so this is all on his website, and I'll send this out.
Oh, we didn't get
it's
the corrections done.
Yeah, when we get it corrected, obviously. But we're dealing with the Kabbalah here. Here's an abstraction of the tree of life with the 10 these 10 nodes that you see here are these sephirah. And so now, what is the underlying geometry of this? Okay, that he came up with. So that the tree of life here is this. He called it a geometrical representation of a heavenly man, Adam Kadmon, heavenly man. So it's the universal paradigm or blueprint for all holistic systems, whether terrestrial or extraterrestrial. Well, that's why I went back and showed you our picture at the beginning with the 18 compactified dimensions that are actually, when you use all the holes, there's only 10 actual real dimensions there. So these are the higher realms. These are the heavenly spheres. These are where all the action takes place. So these 10 emanations or the sephirah are the divine qualities. Okay, again, these are going to be the things that control the entire universe around us. And the first one is called the crown. the Kether, which is God in his primordial subjectivity, the eternal state of divine unity, transcending wisdom, which is God's creative energy, and it's restricted or governed by some sort of laws or principles, or if you
Not
you
Catherine.
algorithms.
Didn't know that we were born until today. So that triggered me.
Yeah,
It's not exactly the same, but still, I was like, I never even knew where Kefir is.
What
I
is
just
the
know
question?
near where he was, near near Pittsburgh, southwest Pittsburgh.
Who do we have? Is there a question?
No, that was me. I didn't realize I wasn't muted.
Okay, okay. So here is this tree of life with the all 10 of these, and you see that they're linked together in different ways. Not everything connects to everything, but they connect to multiple things, as you can see here. And so now what we're going to do is run through this. This is what was left out of the discussion on Kabbalah. That is what is the essence? What makes this mystical? And it was dealing with this tree of life and what that meant. These things all express these different attributes, if you will, that make up things. Now, the thing that comes out of this is this was done probably after Pythagoras. So what in the world did Pythagoras do? Well, Pythagoras had a school of mathematicians, and he decided to deal with the triangular pattern of 10 dots or points, the number 10 again here, which he called tetractys. So these are going to show up as triangular numbers, as arrays
You have to show it, Mark.
of
We didn't get to my corrections on this, I'm sorry.
well,
Just skip
okay.
ahead to show it. It doesn't make any sense.
Okay.
unless you show it. And then go back.
There's another way we can do this to make it also. I'm going to get out of this. I'm going to go back over here to Stephen Phillips. I'm just going to go to his website so you can see this. Why isn't it? So this is from his website. Here is the 10 Sephiroth. Now I just have to be able to go up here. So if you look at the points of intersection of these overlapping circles, you get, if you use those points here, see here's a circle here that's centered at this point, and there's another circle here that's centered at this point. So he went to this point here and drew a little dotted circle. Okay, that you get out of this. So you end up with a bunch of overlapping circles that are centers there of all these things. And then, so if you take a look at the points at the centers of the overlapping circles, or at the ends of their vertical or horizontal, I'm trying to show you down here. Watch this. You'll see in this animation, he's building up a pattern here. So you end up with on top of this what appears to be very simple. You just have this one pattern here in the middle. You can end up with 4 more of these scattered around it.
And that's called the seed of life, which is what the tree of life comes from.
right?
And these are in, ancient temples, European cathedrals, they're everywhere.
And
And it was specialized knowledge, that the priests and the druids, I assume, they all had this knowledge.
so then he constructed, by going up on top of this, there are these so-called 7 regular polygons, and he has one set here and one set there, and he ends up with another construction that leads you to this thing down here. Again, the same idea, the same 4 ovals that we saw before, with the oval here in the middle.
And you can see the tree in that white outline. It
Yeah,
looks like a spider.
Yeah, the tree, you can see the tree here if you look at it. I think he's got an animate. Yeah, there's an animation going on here, which I just triggered. Right. So the idea here,
It just kind of generates all these possibilities. And it's felt that is how the universe is created, in an analogous kind of structure or machine.
right?
It generates these possibilities.
And this led him to what he called the inner tree of life, which is again just blocking out a lot of the complexity you saw there before, and just focusing on what was inside. And then here's his outer and his inner. So here's the tree of life here, and here was his outer, and then here's the inner in here. And then we ended up with even more games here, because here's the tree of life, and it has 10 corners, 22 sides, and 16 triangles for a total of 48 things. This is in mathematics, this would be called a particular type of graph. Okay, it has 48 elements associated with it, and then from this, he came up with a 3D, not a 2D, by trying to crunch it, playing some games. And these 7 regular polygons. Here we have an equilateral triangle, we have a square, we have a pentagon, a hexagon, an octagon, a decagon, and a a 12-sided dodecahedron. No, that's 20.
Is it?
Yeah, decahedron and whatever the 12 is. So he's just constructing these things. But then he gets carried off into this things of playing games with the numbers. So here we have 48. He had 48 entities here, and he breaks it up into 24 and 24, which leads to 13 and 11, which is 24 here, and 24 out here, which is in dealing with these other things. So, and he's continually looking for pattern upon pattern here. This is something that a computer could do a lot more easily than a human being. Okay, but he ends up with an n-sided polygon, and if it has n sides, then he defines something called a yod, which came up to be 6n plus 1. And the number of hexagonal yods in an n-sided polygon, it came up to be 5n, which he's got sketched out here. All of these things are known to the Kabbalists of the 1400s, 1500s, And they went crazy trying to describe these things, you know, and ended up with bigger and bigger numbers, 144, 288, as you can see here, with playing games with these polygons. And the inner tree of life that he had here had 524 of these. So you can see the numbers are getting ridiculous now. But the key thing was he used the letters. Each of the letters had a numerical value, and if you added them all up, then this God name had its own value, and so each of these things had these different values that came up here, and these are all what he called God name numbers for all of these things. This is coming out of this is all in Hebrew, right? There's nothing you know, magical about this, but
Well, there's everything magical.
yeah. And so it went on and on with him doing this. And as you can see, the number value of Yahweh, you know, was a very key one. And each of these had different values as we run through them. So yeah, we end up here with this sort of triangular pattern, which is, there's 70 dots that he's got here, except that he excluded the points of intersection here. The little white dots have all been excluded. And now he's going down to deal with the trunk, which is at the bottom of the tree of life. So he's got a point, a line, a triangle, and a tetrahedron. Here's the tetrahedron. And he uses that to come up with, again, some more geometry that is driving this whole thing. And then, just for completeness, he did the outer tree of life. Which led to all kinds of things. And there's a lot of things here. I can scroll down and you can see there's lots and lots of calculations that got carried out. Try and understand what are the sort of symmetries or patterns were there here. These are the sort of things that you know, really are best left to a computer and not to people. But anyway.
So imagine if you could put the first video we saw together with this, Phillips and
yeah, with what Wolfram is working on. Okay.
Wolfram. Yeah.
So this is the let me get out of this. This is the section that he had on the tree of life.
I'd like to Google
Go,
something.
go ahead.
I just keep talking. Okay.
Okay. What I was going to do.
Get me to Google.
I found what Phillips was doing was not as useful as what, you know, Wolfram was doing, but Phillips was following the traditional Kabbalistic materials, and there's, you know, there's a huge amount of literature on this stuff. And a lot of it is also very cryptic. Okay. Marjorie is searching for something here.
I just say the interesting thing is you show all that. When I was teaching my kids at home, when we were using the Waldorf curriculum, and they do geometry in
Right.
6th grade. They draw a lot of these things in by hand and fill in the circles and figure out how to overlap them and then color in, certain patterns and stuff like that. It's really cool.
It is.
Yeah.
It's a geometric necessity that a circle can be surrounded by 6 circles of the same size at the circumference, if the circumferences are abutting.
If you
And
do,
that's said to be a representation of the week, of the 7 days of the week.
right,
And the 7 classical planets, we count the sun and moon through Saturn. So that's why 7 is considered to be a sacred number.
right.
But
Yeah, the
tree of life is part of a larger, it's like part of a species of sacred geometry shapes. What's the other one?
yeah, the seed of life, the tree of life. What else was there? The inner and outer tree of life.
They did some of the sacred geometry of oh. The hey, the man.
Yeah, this is,
Can you just show this whole page and scroll down?
yeah, we just got to go into
Screen
the
share?
screen share.
Yes.
Here. We're just going to share this so you can see. This is just what you would find looking for a seed of life. You end up with these sorts of geometric figures.
Which you
And
see in a lot of sacred architecture,
Here's the other one. So the picture of the
tree of
man,
life
ancient
is-
picture of man.
This shows the tree of life in these overlapping. So here's 2 circles, then there's 3 overlapping. I mean, it gets very, very deep. And these have been part of jewelry and, all kinds of things. This rainbow one is a nice representation. It just shows how systematic it is. They're not just making it up off the top of their heads. And there's the Vesica piscis.
yeah, you can see, there's a lot of beauty here, but there you can sense there's this order, this greater order, and all I was saying was there's again some underlying set of algorithms for generating all of these different things,
Right.
that are probably quite simple and yet lead to very rich
there's
complicated behavior.
A really nice.
Here's a piece of jewelry here that the seed of life pendant here, as you can see.
And there.
Here we have a seed of life clock. Okay. And so it goes. So there's all kinds of patterns here. The basic pattern I think you can all see is made up of these circles and connecting things in different ways. But it's still very rich for what's going on. Now,
So those points that are the Kabbalists now call the sephirot, or spheres, each one is said to be a microcosm of all the others. So they all are contained, every tree contains an infinite number of trees.
right.
So it's like fractals, or but just in that same way that pattern is kind of generating itself. And so this guy, this Englishman, Phillips, now is he really a Kabbalist? I think he's more of a physicist, isn't he?
Yeah, he's a theoretical physicist, and he had discovered, we talked about the observations of Annie Besant and Leadbeater, Charles Leadbeater, where they did this meditation and came up with quarks and things of that ilk, okay? And what he did was he wrote up a paper on this, and Ron Cowan contacted Stephen in the 1990s timeframe and said that Ron could do the same things that that Besant and Leadbeater had done. So Stephen Phillips came and visited with Bruce, to try and test these things. I'm trying to figure out why I can't get. Let's go here. Here we go. Came and visited, and I'm just going to do another one, so you would see what Phillips did. I just have to go back to screen share. So here we have the sacred nature of the 5 Platonic solids. So what are the 5 Platonic solids that we're talking about here? Hold on one sec while I get here. So there's a tetrahedron, which is an equilateral triangle.
That's like your prison.
Four sides, an octahedron, so that has 8 sides to it of equilateral triangles. The cube has 6 sides. An icosahedron that is made up of the equilateral triangles, and the dodecahedron that is made up of these pentagons here. Okay, so those are the 5 Platonic solids that we came up with. And I'm just going to scroll down here to show you what else. There's a lot of
Okay,
this.
so the dodecahedron has 12 faces.
12, so it is dodecahedron.
I
Okay,
was right.
you're right.
I have.
You can see how I did in geometry. So then he goes through and he shows that the icosahedron
Can we
is
get this
nested.
close to the camera?
Well, here you are. You can just see Marjorie has these die that are dodecahedron, and they have different.
They have the 12 signs of the zodiac, 10 planets plus the north node and the south node, and 12 houses on them. And you can use them as an oracle. You toss them, you ask a question, and get an answer. And we got the moon in Capricorn in the 8th house. So depending on your question, the meaning is all determined by your question. That could be a very profound answer.
Right. So what he's doing here is he's trying to show how these things are related. And so he's got this icosahedron nested inside the octahedron. Okay. And then nested inside the octahedron is the tetrahedron, that's in red. Here you can see. And then the cube is nested inside the tetrahedron. That's in you can see the blue cube here. And then that's nested inside the dodecahedron. And so it goes. So, and he's got an animation you can look at, but he ends up with, again, looking at this, the key thing that Pythagoras dealt with was he had this, what he called first order tetractys. So he took a triangle, but he took one at the top, then he had 2 here, and then he had 3 on this row and 4 on this row. So he had 10 dots total. And 10 was what, as we saw, the Kabbalah keyed on for the tree of life. And this led them to constructing all kinds of things. But he came up with a second order where he took, if you see, he took this first order one and he just created it 1, 2, 3, 4, multiple times here to come up with these other things.
That's that microcosm.
Right. And so the tree of life was captured in the tetrahedron and in this way with the notion of 70. And here he had the 48 hexagonal yods in the face of the tetrahedron and with these platonic not solids, but the octahedron here. Similarly, he went through these things, and it goes on and on and on. You end up with all kinds of patterns that you can see. You can go look at the website for yourself and see all these different things. But the net of it was, just viewing this. Phillips viewed this as an example of the order that came out of this, the perceived order, led him to think of this as being, again, mystical or spiritual in this sense. And so it goes. Now I think I can get out of this. Hold on one sec. Go here to home. I can just touch on what he did for the Sri Rantra, so you could see.
Which comes out of the Hindu system.
So here is the Sri Rantra here, but these are other geometrical manifestations of the same thing coming out of Hinduism. And so what in the world could you do with this? And what you'll see here.
And by the way, the symbol for the heart chakra in Hindu and in Kabbalah is a Magen David, is the upward pointing triangle and the downward pointing triangle. So who influenced who, or is it something objective that they both discovered?
Yeah, the Hindus probably did it first. So you end up with having, this is the most powerful and sacred of all the yantras, the Sri Rantra. And this is what Phillips did then, was he just started to show how to construct one of these things here by taking, you can see these different triangles, and he's moving them around, and he flipped, some are pointing down and some are pointing up. And he ends up with, this thing here, which is actually 5 downward pointing triangles and 4 upward pointing triangles that give you the Sri Rantra here coming out of this. So the idea was simply, playing games here. There is this notion of the golden ratio, which is the golden ratio is actually the square root of 5 plus 1 all divided by 2, or 1.618. And he ended up using this to construct the Sri Rantra, using this idea. And the golden ratio shows up everywhere. And then he tried to show how Fibonacci numbers come up. So Fibonacci numbers are numbers where I start adding, I have 1 bunny rabbit and 1 bunny rabbit. So then at the end of the day, I have 2 bunny rabbits, and then
10 billion.
Then I have 1 plus 2 bunny rabbits. So I have 3 bunny rabbits. Then I have 2 plus 3. So I have 5. And so it goes. So he's going through this as well. So these are the things that weren't covered in the videos that we saw before. They're simply, these are things that were felt to be sacred or not shared with anyone. Okay, that they were they were the secret sauce. If you divulge these things, then that was giving up, a lot of the secret knowledge of the Kabbalah and Hinduism, the Sri Rantra, and that was felt to be a bad thing, and only the priests were able to go do this. I'm, not defending that. I'm just saying that was what was going on. So that was what we wanted to go run through here. Why don't we stop and see if people have any questions? I think this is a different way of looking at all these things, and it may be right, it may be wrong. We should play Socrates here. I don't know what I don't know. It is what it is. But there appears to be a lot of underlying, just call it meta structure, or that is underlying all of this. That's creating the incredible rich complexity that we see all around us. And so it goes.
I'd love to hear more from Nancy and how this was part of the curriculum at the I just went blank.
Was that a
Montessori school.
Montessori?
It's actually Waldorf.
Waldorf.
Okay.
Yeah,
That's
they just
more esoteric, right?
Yeah, I mean, they don't present it to the kids in the esoteric sense. It's literally, you're studying geometry and you're learning how to draw circles, but they measure them out and they draw it like, I mean, literally that's what the kids do. They sit down and they get the instructions on how to draw that, how it correlates to the, like my kids sat there and did you draw out your boxes and you color them in and you figure out the numbers and Fibonacci's, and then I mean they just did stuff. That was just an activity for the day, right? As you figured out how to draw that, or you showed them how to draw it, and then they colored, and came up with different.
That's doing something to their brains and their consciousness, just doing that.
But then it also attaches it to nature, like where do we see six petals and 5 petals are in certain plants, and
That's
a
great.
seed pod and the Fibonacci's number and how it's there, your rows and how you see it's really fascinating. And so for them, it becomes in essence, second nature. Here's all the, Islamic or whatever with all their tiles,
Right.
how all that stuff is just built on top of each other.
Not to mention snowflakes.
Yep. And snowflakes. Right. I mean, that's right there. So this was my instruction book, and this is where they learned. That's exactly what you did. It shows you how to start drawing your circles and how to measure it out. And
Wonderful.
well,
And labyrinths.
yep, all that stuff.
Yeah.
Oh, that's just great. You must have really enjoyed that.
I mean, initially I didn't fully understand, right? It was just like, oh, this is what we teach. And each year builds on that. But then all of a sudden it was like, oh, this is like, they're just learning ancient culture.
Right.
And the premise is that each grade is kind of walking kids through the evolution of man and how that correlates to human evolution on Earth in different phases, and the kids' phases mimics that.
That makes sense.
Yeah, it's really fun.
The fetus goes through the stages of evolution in the womb. The gills at one point, and
right. And the ultimate thing of Steiner is we do the same thing. In the years of sevens, you go through, your state. Even everybody goes through a stage or through different stages. Yeah.
Right. Oh, wonderful.
Yeah.
Very cool. It's great how it brings it back.
Yeah, Bruce, did you want to say anything about Stephen Phillips? You met him and interacted with him in the 90s. Right?
You're muted.
You're muted, Bruce.
Oh, he was a very nice man. He believed that everything was random. I remember he spent quite a bit of time with Ron in a what was it, our motorhome, where he did experiments with Ron. For example, it was he had a wire from one terminal to another, and Stephen could decide whether the current was going that way or this way. And he wanted Ron to be able to tell which way were the electrons going on in the wire.
Mhm.
And he could tell. He had a very high percentage of accuracy. Those are the things I remember.
Yeah, he had a bunch of
Cool.
tests. He wanted to make sure that Ron wasn't simply copying what Annie Besant and Charles Leadbeater,
Right.
and so there was a couple of drawings in their book that he asked for Ron to clarify, and they apparently were draftsman errors. That is, the instructions that Besant and Leadbeater gave to the drafting person to draw the figure. Something got garbled in the translation, and Ron was able to show that basically the 10 strings that they were seeing that make up these subquarks, that the strings are all closed. The strings, it isn't like one gigantic string with 10 loops. It's 10 different strings that are all closed and
Each closed.
next to one another. And in particular, when he looked at the electron, he had 10 of these strings wrapped around the electron. And the key thing was the electron was a torus, was a donut. No one, you can look in physics books till you're blue in the face. They all talk about electrons, but there's never a picture. Ron has the first picture of what an electron looks like.
Yeah.
So, no small accomplishment. Plus the key thing was Ron observed that the electron was covered with these, what he called information blocks, where they were always scanning in these other spaces, in these compactified dimensions, to see what was going on around them, so that they would be in conformance with the laws of electricity and magnetism. It's an electron, so it still has to behave like an electron, and so it was scanning to make sure, am I on the right path? Is this the right thing to do? So
Yeah, one of the interesting things that Ron said about that, he was very excited about that discovery. His sense, well, he saw the electron moving, and then it would disappear and then reappear. And when it was disappeared, he said it expanded to the whole universe and came back.
well, that's what I'm saying. These information scans
Yeah,
go out to the far ends of the universe
yeah,
instantaneously. Okay,
yeah, yeah.
it's you don't need to worry about the speed of light. They're
Yeah.
gone. So
Yeah. He was very excited about it. And he
view of the world. So
yeah. And he said that you could see these little bars that had information after it did the scan. So,
what is this?
well, he said there were little bars that appeared in the electron after it did its scan. And it had the information from the scan.
Yeah, it has to store the information. It has the information blocks have the ability to store bits. Okay, I can't imagine the density of this is incomprehensible, since it's being stored on the surface of the electron.
Yeah.
You think your hard drive has a lot of bits. This is like so many orders of magnitude beyond that. It's not even close.
Yeah.
Yeah.
I remember him being very excited about it.
Right.
Again, it's making me think of those images from the movie The Matrix, with the code streaming down. We're going to work that into the website.
Yeah, it's Yeah, it appears that this is the right level of abstraction, but it wasn't obvious. For example, I didn't really touch on Wolfram at all last year, but I was aware of what he was doing, and I had read his book that he self-published all this stuff because he has so much money at his company. He can self-publish the stuff, but he doesn't write articles now for technical journals. He has his own technical journal that these things go into, and they're all on his website too. So, but the key thing was that he was always viewed as this outcast. Okay, that he'd lost interest in high energy physics and theoretical physics, and how could you be doing something so mundane as messing around with computers? And his intuition being that it was, and his energy to be able to go do what he did, it led him to write this book, which he called A New Kind of Science. And I got the book and I read it, and it had a lot of descriptions of pictures like he was showing there, okay, in his talk. And I said he was all excited over, this picture rather than the other 37 pictures that he threw out. And for the life of me, I couldn't figure out what he was excited over. But here we are. That talk that you saw was 10 years ago, okay, or not more than that, 12 years ago, 2010, and so he's advanced a long way since then with a lot more structure, and is attracting some really incredible people that are going to flesh out these ideas, and we'll see where they go. He could be wrong, but to me, it has more of the ring of truth than anything else, and it's simple enough that it could work. Is the thing. So we'll see what happens.
To me, he's like Darcy Wentworth Thompson, that guy that Bart and I both read many years ago, and that was one of the things we discovered we had in common. He's like him cubed.
Yeah, well, remember he did get the, he was on the faculty of Caltech in their theoretical physics department, which is the strongest group on planet Earth. And he was also had a position at the Institute for Advanced Studies in Princeton, which is where Einstein and Gödel both were. Okay, and he walked away from all of this to do what he was doing. And a lot of people said, well, how could you possibly do that? Well, he did it in part because he thought there was something there with the computational side, and now he's coming back and trying to do a whole new foundation of physics, but based on algorithms, and we'll see how it shakes out. As you can see, he's describing something that's more fundamental than the space and time that we have around us. So, go figure. Anyway, with that, any more questions from anybody?
Or
Well,
comment.
I have a question and I have a comment. So my question is, on the seed of life, graphical image representation, has anybody tried to bridge the gap between breaking down a seed of any kind to get close to that geometry, or is there a big gap between what we can do with the tools we have today and getting to that?
I think that the thing about these algorithms is they allow you to evolve. Okay, so you can start with the seed and then it will grow into the tree. When you actually look at what the algorithm is. But to the best of my knowledge, I don't know that anyone's done that. But I'm just saying that's what I would look for is something that encompasses that notion of evolution.
I think it's a holographic thing myself, that they exist within one another.
That's interesting. The thing for me years ago, I want to say it was about 2003 or 4, I was involved with a company called PV Wave, and it was a series of mathematical subroutines and algorithms that you could apply to things. And I got to watch people that used to print out green bar paper of all their efforts, science and math people. And then with applying these algorithms, all of a sudden they could take the ones and zeros and turn them into one of my favorite examples was taking raw data from a heartbeat or the heart and actually creating an animation of a person's heart from the raw data into a visual animation of a human heart. And
Wow.
that for me was like a mind blower, to go from green bar paper of numbers to an actual animation of a person's heart.
Yeah. I mean, just Cheryl, on that particular thing, I had this heart attack where I had a stent put in April of 2016. And, but there was a guy I was working with who came out of the General Electric labs up in Schenectady, New York, Albany, New York, who was an expert in superconductors, okay? And so he created a system where he had an array of superconductor sensors that he just suspended. I went to go see him after my event, and he suspended these things over my chest. Okay? And the reality is that your the muscles around your heart have electrical currents in them that actually drive the muscles, and it leads to a very strong magnetic field around your heart. And so these superconductor sensors were able to sense that, and he could construct a complete picture of my heart beating, and he could see whatever the damage was. I was able to catch it very quickly. So there was, I'll just say a small amount of damage, 10% or so. And but the net of it was that I went to go see him after my rehab program, which was, I guess, 3 months, maybe 3 or 4 times a week on some treadmills and elliptical machines, and redid everything. And it all is the same pictures, but he had, a bunch of metrics there. And initially when I went to see him, 7 metrics, I was inbound on 3 of them and out of bound on 4 of them. And after my rehab program, I was inbound on all 7. Okay.
Wow. Wow.
In range, and the heart was beating away and so forth. And, and so that was something that you could actually do this stuff now, other than for the superconductor array. You could actually do the whole thing with an iPad. Okay, the algorithms are not that crazy, and you'd end up wanting to use neural networks to get rid of a lot of the electrical. There's a lot of grounding problems there with all kinds of crazy currents that you could swamp what's really going on. So it was amazing what he did, but we could do a lot better job now than then. So anyway, that was what that's what Wolfram is making possible with all of the software that he's generated, is making things like that be very, very easy to do.
Yeah, it's pretty remarkable.
Yeah.
Really inspirational.
What do you want to show this?
I want to show something.
RJ wants to show something. Hold on.
I went to look for some in the kitchen and I couldn't find it quickly. Okay, here, can we just show this page again?
Yeah. Hold on. Okay, so these are star anise.
I always said anise.
Anise.
Oh yeah, that's so cool.
But just what you were asking about, Cheryl.
Yeah, I love it. I love it. I love it.
Answer came to my mind.
Oh, that's great.
Yeah.
Beautiful.
Yeah, it is beautiful. I always liked that too.
Too, I like it.
Yeah.
But it's almost like a pun or something, the way. he-
Yeah, yeah.
Yeah. Okay. So
Very-
let's get out of this.
Oh,
Anything else? Any other questions, comments, whatever?
Bruce, I want to ask you a question. You was, Ron was, you guys were twins
Yeah, we're identical twins.
and were like, what, how, like the connection between the two of you?
There's-
Obviously, you're saying like he got a bit more of the, that ability than you had, but the connection between the two of you was pretty profound. And what about your connection now that he's gone? Do you still feel?
Oh no,
connected?
he's gone. He's gone into another lifetime altogether. Whatever was happening in the previous life doesn't apply anymore. So she's just gone.
So you don't get
Well,
any,
Nothing. No.
no.
I saw him in the Bardo between when he died and when he was reborn.
Yeah.
I had that. But earlier in life, we were both very telepathic. And we were used to one starting a sentence and the other one finishing it, things like that.
Uh-huh. Wow.
Yeah, and Ron really focused on his clairvoyance and being able to see down, and not simply into the microcosm, but also out into the depths of interstellar space in between, galaxies, and he was able to, as we'll see when we go through the cosmology, he was able to go back to where this iteration of the universe started up again, and it was a big bounce, and he got very detailed readings, and some of the pictures are posted there on the website of what the bounce looked like, because it's this crazy thing where everything is crunched down, this quote unquote small entity. Well, then if it's crunched down, what's outside of it? Because that means that space and time are crunched down into whatever is there. So there's something else outside that this is all in, and I have no idea what that is. But he was able to, to go through that, and that's what he really focused on. And he was able to look. I asked him to look back into my life to see what he saw other lifetimes, and he had some thoughts there from. I've been incarnated apparently many times. So.
Cool.
Yeah.
Interesting. Interesting.
So.
I don't know. What were you saying?
Oh, he gave me a lot of information about my previous lifetime, which helped solve a lot of problems that I encountered in trying to get past them. He was super good. But the other thing about him was he was extremely bright. Like I remember we were teaching this young lady, Ron wanted me to teach her about bookkeeping, which because I'm a bookkeeper, I could do that. But then they got into this really different kind of accounting that I didn't know anything about at all. So she had this textbook, and I read it, and I said, no, I can't understand it. I don't know what it means. And Ron was sitting in the other room watching TV while I was trying to teach this young lady. And I said, okay, well, let's get the brain in here. He could read the paragraph, understand it, and then explain it in good English in about 5 minutes. He had that ability. It just like, it was amazing. He was very bright.
He was also a very good artist, which was important because there's no instruments that you have for making the observations that he was
Right.
talking about. So that's why you see all these sketches, but he went to great lengths to make sure that he was correctly sketching what it was he was observing.
Yeah.
And would cross-check in numerous ways. So that's, you know, his only comment to me was, how come I'm the only one that believes him? I said, it has the ring of truth, you know, what you're seeing. So
Bruce, are you artistic in that way? Or can you draw and or express yourself in an artistic way?
I used to be when we were younger. Both of us were very good artists. But
Okay.
I sort of, I didn't keep it up, but he did.
Oh, wow. Wow. That's neat.
Yeah. The other ability he had the ability to look at the history of anyone. He could go into their mind and he could read what happened to them in previous lives.
Wow. Wow.
Yeah. He sort of kept it private because he said he didn't like going there, but he sure could do it. And he sure did in my previous life, and it was a big help.
Was there something that like if you guys were identical twins, was there an event that happened to him that made his ability expand that didn't happen to you?
No, he was a different soul. He was a very ancient soul, just like he's been around for a very, very, very long time, and he had these abilities because he's done them before, you know? So they're just a natural part of his mind.
It wasn't like he was struck by lightning and you weren't.
No such luck.
But Bruce went on to be acknowledged for achieving enlightenment, which Ron was not.
Right.
Yeah.
You just took different paths, right? Your life path was different.
Oh, it was very different. I mean, everyone thought we were identical, but we had no problem.
You.
yeah.
But these abilities are called siddhis in the Buddhist.
Yeah, they are.
Yeah, in the Yoga Sutras, yeah, CD,
Right.
yeah.
And they are considered to be a distraction from the path to enlightenment.
Yeah, they're like parlor tricks, is the way that Patanjali.
Well, that's not quite true. What happens is that you can have from previous lives these abilities arise, and they're considered a distraction until you find the deeper realities, and then all the cities are already present.
Right.
Right.
They're just a distraction in trying to get there. But after you arrive, all of it's there. And it's a very different experience of reality.
Yeah, you're sensing the true reality. What's really,
that's right.
really
Yeah.
the essence.
Yeah.
Sounds like he spent more time in these thought experiments and observations than putting it all together and going after total enlightenment. Is that fair to say?
Well, the dimension that I sort of followed is what I got from my guru. When I connected to him, there's powerful love mind he had. And when I first met him, I saw his mind. It was very expansive, very different. And so, but basically, he showed me the vast realities of heart mind, love mind, and compassion, and all that. And basically, what happens is that there's an innate already reality of understanding the mind, and it's full of incredible certainty and vivid awareness. Like it's very different, and in a sense, the reason I took that direction because he showed me that's what was there. he showed me that that was there. And so my mind picked up on that and where we went. I mean, he was a very remarkable, when I was working through my family conditioning, in the middle of the night, he'd give me a dream and then he'd wake me up and we'd talk about the dream telepathically. And that was so he was able to show me things about my family conditioning that it would have taken me years to find out. So my main unfoldment was in that direction.
And all of my interactions with Ron, he was very much focused on these observations, and it really wasn't focused on what Bruce is talking about. He just we kept drilling down and trying to. That's why we have the pictures I can show you, and so forth, to try and present a kind of a modern physics structure, or metaphors or pictures that would be what modern science attaches labels to, things like quarks and subquarks and so forth. Ron was just enamored over drilling into that, and I was there to just try and coach and add some structure to it as I could. So
yeah, he found out. He told me that you're a big help because you kind of told him to look in certain places that he wouldn't have done.
There are too many things to look at, so I pushed him to look for the Higgs boson. So when the universe is created, okay, initially everything is totally symmetric, and by symmetric I mean there's no mass. Everything is just absolutely crystal simple. But there's a so-called breaking of the symmetry, and that creates this funny boson called the Higgs boson, which these guys got the Nobel Prize for in 2012. And the Higgs boson is there in both matter and in dark matter, in both of them. Okay, Ron, I pushed him to look for both of them because I couldn't believe it was just for matter. And he found both of them right there. And once the Higgs boson kicked in as an actual particle, it gave mass to everything. Okay, that's why it's called the God particle, is because without it there would be no mass for anything whatsoever. And
it was like the gauge or something, right?
Yeah, it's what's called a scalar, but it multiplies everything in the universe. Everything in the universe gets scaled by this Higgs boson, by its intrinsic mass or its intrinsic energy. Mass and energy are the same thing. So it goes. So those are some of the things we worked on.
Right.
Anybody else? I'm going to wrap it up otherwise.
Thank
That
you.
it? Okay, then we'll get everybody next week. We'll see if
Thank
when
you
the
for
world,
being with us.
Thank you.
yeah,
Thank you.
we'll see what happens in the Ukraine. That's nothing good there.
Yeah, God.
Anyway, have a great weekend.
Yeah.
Bye-bye.
Good night. Good night.
Thank you, everybody.
Well, everyone.
Say that.
Yep.